reagents in indicum mediated cyclopentanoid formation. So such reactions, they are usually now carried out in different type of solvent. There are another benign solvent, that is carbon dioxide. Many organic reactions also be carried out in such. So what we learned, that safer solvents and auxiliaries recommends that the process of synthesis be maximally be reduced, and whenever possible avoid these use of these hazardous and toxic chemicals. Now, uh, let me say a few words in green chemistry. Uh, what is green chemistry? Now, according to the Environmental Protection Agency, definition of green chemistry is like this. It is defined as chemistry that designs chemical products and processes. They are harmless to the environment, thus preventing the formulation of pollution. Now, green chemistry is not a separate scientific discipline, but a responsible interdisciplinary approach to science based on chemical, ecological, and social responsibility, which enables creativity and the advancement of innovative research. As a propulsive area of research, it tries to find and maintain its balance between the use of neutral resources, economic growth, and environmental conservation. Now, to be called green, each reaction should have three green components: solvents, reagents or catalysts, and energy consumption. So green or sustainable chemistry is based on 12 principles that can be used to create or recreate materials, reactions, and processes that are safer for human health. And the process of green chemistry developed, the data include mainly all areas of chemistry, including organic, inorganic, biochemical, polymeric, toxicological, environmental, physical, technology, etc. So these few words I have to stop here. But lastly, my heartiest thanks to the members of the organizer who have tried their level best to be to organize such a seminar under very unfavorable and pandemic situation. So I believe that not only the students but the teachers also will be benefited from the illuminating lectures of Dr. Bandyopadhyay. Thank you very much.
Thank you, sir. Now, I am inviting respected IQAC coordinator of Rishi Bankim Chandra College, Dr. Moinak Rai, for his brief introduction about today's webinar.
Thank you. Am I audible?
Yes.
Yes.
This is a matter of pride, great pride rather, to be invited in this webinar to address and welcome the learned audience of the webinar on organic reactions in water, organized jointly by the Department of Chemistry and IQAC cell of Rishi Bankim Chandra College. Being the coordinator of the IQAC cell, I would foremost like to welcome the speaker, Dr. Chandrakanta Bandyopadhyay, Associate Professor of Ramakrishna Mission Vivekananda Centenary College. I would also like to welcome our principal, who is also a regular teacher of this department and takes classes almost regularly in spite of his extremely busy administrative schedule. I would also like to welcome the participants, including the students of our college who joined us today's webinar. I believe this webinar would be immensely attractive as well as effective to them since the topic has been selected keeping their curriculum in mind. I would also like to take the opportunity to congratulate the dedicated faculties of this department. I personally know them very well. This is not just another ceremonial webinar, rather, it shows the continuous battle to uphold the academic interest of the students in this new normal situation. I like to congratulate this energetic young brigade. I believe this webinar will come to the immense help of our dear students as well as to our colleagues. I wish this webinar a grand success. Thanking you all to spare this odd man out a few minutes. Thank you.
Thank you, sir. Finally, I request Dr. Sheikh Hannan Mundol, Associate Professor of Chemistry Department, to introduce our distinguished speaker, Dr. Chandrakant Bandyopadhyay, to our esteemed audience. Hannan, please take over.
Hello. Am I audible?
Yes.
Hello. Good evening, everyone. I am feeling honored to introduce Dr. Chandrakant Bandyopadhyay. He did his graduation and post-graduation both from the University of Calcutta. He received his PhD degree also from the University of Calcutta. He has done his postdoctoral research work in Taiwan. In the year 1984, he joined the Department of Chemistry, Ramakrishna Mission, Vivekananda Centenary College, Lahore, as a lecturer. Presently, he is serving as the associate professor and head in the same department and engaged in teaching undergraduate, postgraduate courses and doing independent research work in the department, even with meager laboratory facilities. Till date, he has successfully completed 2 minor research projects from UGC, 4 major projects from UGC, DBT, and CSIR. His major research interest covers synthetic organic chemistry. He has published all together 67 research papers in peer-reviewed national and international journals, of which 52 from his college laboratory. He guided 5 students for their PhD degrees from the University of Calcutta. Besides this, he has authored a book entitled An Insight into Green Chemistry in May 2019. Second edition of this book is in press and is going to publish very soon. He is the recipient of Professor Navneet Rao Best Teacher Award in the year 2013 by A.V. Ramarao Research Foundation, Hyderabad. He has also received Postal Chemical Research Society Award, Category C in 2015. Now, I request Dr. Chandrakant Bandyopadhyay to deliver his talk on organic reactions in water. Dr. Bandyopadhyay, please proceed. Dr. Bandyopadhyay. Hello, Dr. Bandyopadhyay.
Thank you,
Welcome.
Hannan sir, for your
Welcome.
kind words of introduction. At first, I like to express my sincere thanks and gratitude to the organizing committee, and especially Sanjeev Da and Gopa, who is my classmate, for inviting me and giving me this opportunity to share a few words with you. Now I am going to share with you the slides. Is it visible in the screen? My slides? Is it visible in the screen? Please.
No,
না না
not yet.
দেখা যাচ্ছে না
Not
দেখা
yet.
যাচ্ছে না
Okay. So let me just share. Now?
হ্যাঁ,
Yes,
এইবার
yes.
এইবার
Yes, yes.
Okay.
হ্যাঁ,
Okay, okay.
Is it okay now?
Okay. So let us start. Respected principal sir, respected other teachers, respected other distinguished delegates, and my dear students. At the very beginning, I like to express my sincere thanks and gratitude for inviting me and giving me this opportunity. The today's lecture is on the very minute part of green chemistry. Green chemistry is a very vast area, of which I'm going to discuss today a very small area, that is on the organic reactions in water. But before entering into that, I like to share a few words about the green chemistry, which has a history of about 60 years. In 1962, Rachel Carson, who was an environmentalist as well as a biologist, in her book Silent Spring, she warned the people about the danger of the insecticides. She showed that in the eggs of the birds, the insecticides were there, and that was coming from the food chain. The insecticides, those we spray on the paddy fields and corn fields, those are coming through the food chain into the animals and then into the eggs of the birds. From that warning, in 1969, first US government, they introduced one act that is called NEPA, National Environment Policy Act. And in that act, it was warned that it was due to this fact that it is to maintain the conditions that the nature and animal can exist with productive harmony. It means they will not harm each other. They should live with productive harmony. And the next year formed an agency that is called the EPA, Environmental Protection Agency. The first important job that the EPA did, that was to ban the DDT. And then another thing they did, that is, they warned all the chemical industries to clean up their waste materials, their effluents, that is all the toxic materials from the effluent materials that are to be cleaned first, and then they can throw it into the environment. Under this condition, the chemists entered into the field, and they thought in some other way. Instead of cleaning the toxic material, they thought that if the process can be changed, that is where the toxic materials are going to form, if that can be stopped, that is, instead of pollution remediation, chemists suggested to pollution prevention. And after that, in 1990, George W. Bush, he enforced one act, that is the Pollution Prevention Act, that nobody is allowed to generate any pollution. But if you impose anything, then you have to give some incentive. And that's why in 1995, Bill Clinton announced the Presidential Green Chemistry Challenge Award. It is given in 5 different areas. And from the next year, the industries and people started to get this award. I'm not going into those in detail, but the revolution in green chemistry that started in 1998 with the promulgation of the 12 principles of green chemistry by J.C. Warner and Paul Anastas. Paul Anastas was the head of the Research and Development Division of EPA. And these 12 principles, I'm not going to discuss these. These are very popular now today. I like to mention 2 things for the younger generation. That is one thing, use of renewable raw materials or feedstock. You often heard a term that is sustainable development. What does it mean, sustainable development? That is, the developments that we can do today, we have to be sure that those developments can be carried out in future. So this is the sustainable development, that is, the developments can be sustained. It is not desirable at all to meet the expense or to meet the needs of the present day with the at the expense of the interest of the future generation. It means that today we have petroleum products, we have fossil fuels. If we consume all those and we do our developments, then in the future generations will not get that. For their developments, they will not get those petroleum products because the fossil fuels, although they are generated naturally, but it takes millions and millions of years. So that cannot be destroyed today. Then what should we do? We should take some renewable raw materials. That is, or we can say that we should take those materials which can be reused. So as an energy source, if you can use some other types of compounds, say vegetable oil, animal fats, if you can use these things as the raw materials, this can be generated, this can be reused, because by system of cultivation or by the system of production, this can be readily generated. So whatever we want to do developments, that should be sustainable. I am just considering about in the field of chemistry, but in the field of science, there are many ways, many areas are there where all are to be considered, that developments can be done, only those which are sustainable. So now, as a chemist, when we are in the department of chemistry, so we are concerned with the reactions only. And from the long time, from the time of Aristotle, it was known that the reactions can only be done in solution phase. It was the earlier concept. And now we have come to day when we came to know that the reactions can be done in solid phase, under solid state condition or solid phase reactions, those can be performed today. But still, what we do today, the majority of the reactions are carried out in solvents. Now, as an organic chemist, again, if you consider about the solvent, and another thing I should mention, that if you consider the chemical reactions, say 100 milligram of component A, 100 milligram of component B, and then you are using about 20 to 25 milliliter of solvent. If that solvent be the source of pollution, then what will happen? Instead of the compounds that are going to be formed, or from where we are going to form those desired compounds, we are making the pollution from the solvents, because the major component of the reaction is the solvent. So that solvent should be controlled. And if you can use some benign solvent means those solvents which are not harmful to the society, harmful to the environment. If you can use this type of solvent, then that will be very much helpful. So today we are going to consider how these benign solvents can be used. There are some benign solvents, those are considered in the green chemistry, but they are benign in different aspects, as our principal sir was considering about supercritical carbon dioxide, water, some ionic liquids, some fluorous solvents, polyethylene glycols. All these are now considered as benign solvents. But the most cheap solvent is water. It's about the organic chemist. As an organic chemist, what we do, we actually use benzene, toluene, or other chloroform, DCM, carbon tetrachloride, these types of solvents. And all these solvents are, some are carcinogenic, some the fluorocarbons can deplete ozone layers, and most of the solvents are volatile. They enters into the air and causes inhalation problem. So what the organic chemists do? Should they stop doing reactions? Definitely not. Then what should they do? They should take lesson from the nature. What the lesson does, nature does, the nature performs all her synthesis. Thousands of reactions are going on in nature. Organic reactions are going on in nature, but all are in water. So if nature can do so many reactions, so many critical reactions, then why not the organic chemists? They should take lesson from the nature. And we know that water is the medium of communication. That is called the lingua franca of life on our planet. So we should take lesson from the nature and we should proceed. People has done that. In 1939, Hoffenstrauss, he performed a reaction with cyclopentadiene and methyl vinyl ketone or methyl acrylate and showed that these reactions was accomplished in water with more efficiency than in other organic solvents, and also the endo-exo ratio was also improved. The endo product was increased to large extent. Then another reaction here is the 9-hydroxymethyl anthracene in ethyl malimide. These reactions, if you perform these reactions in water, it is about 200 times faster than in acetonitrile. If you perform a reactions of cyclopentadiene with parabenzoquinone, the activation energy was found to decrease if you change from hexane to water by 5.8 kilocalorie per mole, or from acetonitrile to water by 4.8 kilocalorie per mole. It means the rate enhancement takes place. Now the question arises, why? Why water is doing this? So we have to enter into the water, not by stopping the breath, but we have to enter into the water by knowing its properties. What are the properties those have in water? We know, but still I am going to discuss a little. Water is liquid within a long range of temperature from 0 degree to 100 degree. It is capable of doing extensive hydrogen bonding, all are known to us. Another property, high heat capacity. I just like to tell a few words about it. High heat capacity. We know what is heat capacity. The amount of heat required to increase the temperature by 1 degree. Suppose you are doing a reactions, exothermic reactions, an industrial scale. It means large amount of heat is produced. Now, if you can perform that reactions in water, then what will happen? The temperature rise will be small because water has a high heat capacity. It will consume much amount of heat, but the rise in temperature will be small. And again, we know that the decomposition of a compound depends on the temperature because every compound has a particular decomposition temperature. So now you think, if you can perform a reaction in water, and exothermic reactions, large-scale exothermic reactions in water, as the temperature rise will be small, so definitely the compound will not be decomposed. So we can make the large-scale exothermic reactions comfortably in water because of its high heat capacity. Then it has a high dielectric constant, which stabilizes the polar transition states. Then you consider the optimum oxygen solubility, which allows the aquatic animals to survive. It is cheap and readily available. It is all known. The last property is the most important. That is the high cohesive energy density. Students may not be aware with this term, high cohesive energy density. I'd like to discuss it. What is density? Density is mass by volume. That is gram per cc. That is density. What is energy density? Energy by volume. What is cohesive energy density? Cohesive energy by volume. How can you define it? So cohesive energy, suppose you are considering a solvent. You consider a molecule in the bulk of the solvent. You want to take up one molecule from the bulk. So you have to give some energy. So that amount of energy required to take one molecule of that solvent from the bulk, that is the amount of energy. You have got the cohesive energy. When you convert it on density means by volume. By volume means divided by the volume of the cavity created due to removal of that molecule. I'm repeating again. I'm repeating this definition like this. Cohesive energy density is the amount of energy required to take up one molecule from the bulk divided by the volume of the cavity created due to removal of that molecule. So the unit will be like calories per cc. Now I am showing you a chart of cohesive energy density, CED values of different solvents. And you will be surprised to see that water has 50.2 calorie per cc. Then methanol, then member is methanol, come up with the common solvents we have considered, 208.8. And if you come to hexane, it is 52.4. That is, water has the highest cohesive energy density and is a very big value, high value. And practically this value, this high cohesive energy density of water is responsible for those reactions that we are getting today in water. I am going to discuss it in detail. So this is the cohesive energy density is the most important thing. Now, before discussing all these things, I like to classify the organic reactions in water in aqueous medium. It can be classified in some ways. First one is in-water reaction. Another is on-water reactions. I like to add one thing more, that is with-water reaction. What are these? In-water reactions means when the compounds, when the reactants are soluble in water. It is, for definition, it is considered as 100%, but in reality, all are not 100%. Their solubility, if some solubility is there, then we can consider it as in-water reaction. Whatever, by definition, it has been told that when the components are soluble in water, but the product is insoluble, that means the reaction will go on in water and it will be precipitated. This is the in-water reaction. And in on-water reaction is very surprising. Starting materials are insoluble. Components, the reactants are insoluble. The product is insoluble. But the reaction is going on. It is very surprising, and I shall discuss it, how it is going on. Some conditions are there. Under that conditions, these reactions can occur. So now the question arises. We have gone through the properties of water, and we have learned what type. Another, I wanted to tell you that with water reactions, that is if water be the reactant, like acetyl chloride plus water is equal to acetic acid plus HCl. Just like that, water can act as a whatever it may be. Now we want to tell you that when we are going to consider the effect of water, we have learned the properties of water. We have tried to analyze those, and now we are trying to consider the different factors, those controlling the organic reactions in water. These factors are like this: hydrophobic effect, hydrogen bonding, polar effect, Marcus transphase hydrogen bonding involving micelle medium or micelle formation. Now, let us start with this. Say hydrophobic effect. What is hydrophobic effect? Whenever you are going to consider a new term, try to analyze that. Hydrophobic effect. Hydro means associated with water. Phobic means hating, that is repelling. So what will be the hydrophobic effect? Hydrophobic effect will be the repulsion of non-polar substance by water. And here I have shown you a dissection of the micelle. Actually, if you consider a soap particle has a long hydrophobic chain, because soaps are long chain sodium or potassium salts of long chain fatty acids. Long chain fatty acids means these are the long chain of the hydrocarbon, and here is the sodium carboxylate or potassium carboxylate. These are the polar end. When you place them in water, what happens? Those hydrophobic chains, they will be repelled by water. That is the hydrophobic effect, repelled by water. And due to that repulsion, or to minimize those repulsion, they will form a cluster, keeping the polar end at the top, and they will make such globular shape. And these are the micelles. I like to tell you a simple way. Not I am going to micelle today. I want to tell you a simple example. Suppose in a test tube, you have taken half test tube water, and then you just put one drop of oil. You shake vigorously, keeping the mouth stoppered. You shake vigorously. What will you obtain? You will find that the drop has broken into droplets and the water looks hazy. Then you allow to settle for some time. What you will find? You will find again the water is clear. The droplet has combined together and to form the drop of oil. So why it is happening? It is also a case of hydrophobic effect. The water molecules are repelling the tiny droplets, and those tiny droplets, to minimize the repulsion, they collide with each other, they mixed with each other, and so that the surface gradually decreases. When they are in the droplet forms, surface area increases. When they are gradually colliding, then the surface area will gradually decrease. So to minimize the surface area, again the droplets will form the drop, and this way the hydrophobic effect can be considered. Now you think about it, the reactions that I have shown you earlier, that these reactions can be performed in water 200 times faster in acetonitrile. Here the activation energy is decreased, and that's why the rates of the reactions in water is 4500 times faster when you change from hexane to water, and here 970 times faster. Now the question arises, how these reactions are going on? Because if we consider hydrophobic effect, then these are the organic materials. These are non-polar. You can consider this the organic matter. They are relatively non-polar. So water may not, the solubilities may not high. What will happen? They will be repelled by water and they will come closer. Okay, if they come close to each other, will they react? Then if we mix them together, will they react? Definitely not, because to perform the reactions, we have to gain the activation energy. From where this activation energy is coming? That is very interesting. And that is also from that hydrophobic effect. But I'd like to tell you in this way. Suppose these are the components. These are these two components. Suppose these two components or these two components, these are the small aggregates, hydrophobic aggregates we have considered as AB. Two components. When these components are here, the water molecules surrounding this, they form lateral hydrogen bonding. It is very easy to see, but difficult to realize what is happening inside. What is happening? Earlier we have told you that water has a very high cohesive energy density. You realize it. It means the water molecules try to stay in a very compact condition. They try to attract each other very much. And under that condition, you have put some foreign elements, foreign matter into them. What will happen? They are trying to come closer, and you have put some hydrophobic matter inside so that they will make a large pressure over it. If you cannot understand, I can tell you a very small, on example that we are all acquainted with that. In the train, today train is stopped, but we all have the experience of traveling in train, local trains. You just consider in the office time local train, in the window side, a party are playing on cards. They are very much interactive to each other, and they are trying to interact with them only, and nobody is allowed to enter into their periphery. But if a people by force enter into it, what will happen? Those people who are playing the cards, they will throw some words so that the external body who has entered into them, they get excited, and then some different matters may happen as they are going to be excited, so they may be reactive. So now you consider here also, when these water molecules are playing the cards, they have a very high cohesive energy density, and when you place an hydrophobic aggregates in them, these water molecules is not preferring it. It is always trying to create high pressure over it, and that pressure is actually giving the activation energy of the reaction. Now the question arises, okay, the activation energy may be obtained from the pressure created by these water molecules because of its high CD values. Then why the rate enhancement? If it gets the activation energy, then it should react as it was in the case of the organic solvents. But why in water the rate enhancement takes place? To enhance the rate, definitely the activation energy is to be decreased. Actually, what happens, I shall discuss it in the polarity section when I shall discuss the polarity, that in the transition state, the hydrophobicity is lost in the reaction sites. And those transition states will be stabilized as hydrophobicity is lost, so some polar conditions has achieved. So the water molecule will solvate the transition state, and the transition state energy will be decreased. And that's why the rate of the reactions also increases. Here the why the rate accelerations that has been considered. The reactive sites of activated complex lose their hydrophobic character entirely and will be stabilized by water. That is, the activation energy is decreased. Now we are coming to another aspect, that is the hydrogen bonding effect. Second effect, that is the hydrogen bonding effect. We all know that hydrogen bonding takes place oxygen ... hydrogen like this, CN like this. And here methyl vinyl ketone, here oxygen is here nitrogen is here. So the extent of hydrogen bonding will be greater with oxygen. Here is the reaction, you see, Diels-Celder reactions. You know that homodiene going to react with LUMO-dienophile. So if the LUMO is stabilized by hydrogen bonding, then the rate of reactions will increase. Here the LUMO oxygen is stabilized. That's why 2.8 kilocalorie per mole is decreased amount of energy if we move from gas to water. For cyanide, as nitrogen is here, it is that stabilization is little less. That's why 1.5 kilocalorie per mole. Now, it is the homodiene, LUMO-dienophile that has been shown here. Now, if in this example, it is the isoprene, 2-methyl-1,3-butadiene, there is no polar end. As in the previous case, there was oxygen or nitrogen. So here, the only effect is hydrophobic effect that is operating. But in this case, as both oxygen, nitrogen polar groups are there, so it may be considered as the combination of hydrophobic effect and hydrogen bonding effect. Both effects are operative. Now I am taking you with some more examples, like effect of solvent change. How these Diels-Celder reactions are influenced by effect of solvent change. The same Diels-Celder reactions, first 1 and 2, you say. See, you are changing the solvent from isooctane to water. When you are changing the solvent from isooctane to water, here is no hydrogen bonding, no considerable hydrophobic effect because CED value is low. The higher the CED value, higher will be the hydrophobic effect. So if you change it to water, then the hydrophobic effect as well as the hydrogen bonding will be increased and the rate enhancement is 31. Whereas if you use methanol to water, methanol has hydrogen bonding and hydrophobic effect, relative increase in hydrophobic effect is also less from methanol to water. Then the rate enhancement is also less. If you change it from methanol to water, it will be 14.8. But for isooctane to water, it will be 31. Similarly, isooctane to water for this reaction, this set of reactions, isooctane to water 740, methanol to water 58. Again, this set of reactions, acetonitrile to water 290. Because here both cases, both things are happening, hydrophobic effect as well as polar effect. Here only hydrophobic effect. Polar effect was there because hydrogen bonding was there. That's why the rate enhancement is lesser. Now, if we consider the effect of dipolarophile, here is a hydrocarbon, here is a hydrocarbon, and here the solvent change is same. Say acetonitrile to water we are considering here. Now, if you consider the hydrocarbon, here only 15 or 5. Here cyanide, only 6. Ester, alpha beta unsaturated ester, 12. Alkyne, ester group with some alkyne, only rate enhancement 7. Some ketone, 50. There is some ketone, 45. So these are some of the examples of the dipolarophiles. I am just taking a few of them in the next slide. You see, this is the hydrocarbon, this is the acrylonitrile, this is ester, this is ketone. These 4 types are considered. If you look at the relative rate enhancement from acetonitrile to solvent, you will find here it is 15, here it is 6, here 12, here 59. But if we consider these 2, there are 2 oxygen, so extent of hydrogen bonding should be greater here. So if hydrogen bonding should be greater here, so the rate enhancement should be greater. But here a rate enhancement is smaller. You see 12, here it is 59. Why? Again you see, here is the ester, alpha beta unsaturated with some azomethane ylide. It is a Whitzian cycloadditions reactions. It is not Diels-Celder reactions. Here 1,3-dipolar addition reactions. Here is the azomethane ylide and methyl acrylate. All these are azomethane ylides. And here it is the methyl acrylate ester, 15.3, ketone 202. Here again another ketone 164. So whenever we are going to consider the ketones, the rate enhancement is higher, but for the ester it is smaller. Again you see, if you consider the alkyne system with ketone, rate enhancement 154. Alkyne system with ester, rate enhancement is 12.7. Again for the ketone, rate enhancement is higher. So whenever we are doing some cycloadditions reaction with ketone, we are getting good results in water. That's why it is called water super. conjugated vinyl or alkynyl ketones showed high rate enhancement in water and are called water super. So if you want to do any Diels-Alder reaction in water, try to choose your dienophile as some ketones that will give you good result in water. But the question arises, why? Why this ketone is behaving in this way? Practically, what we have learned about the hydrogen bonding, that is the single bonded hydrogen bonding. We are very much interested with just a single hydrogen bond, oxygen ... hydrogen, like that. But another type of hydrogen bonding may occur, that is the growth of strong structured water cluster. What is that? Growth of strong structured water cluster. It means there is a concert. There is a concert of water. Now the musical concert is going on in some other side. And here I just like to tell you what is that concert. Suppose a musical suite is going on. So many instruments are playing in the same rhythm. And that's why the music is so much beautiful to us. But if you can simply change one of the instrument and you allow that instrument to run or to play in some other tune, what will happen? If you allow one instrument to play in some different tune, different loy or different sur, what will happen? It means the total musical suite will be destroyed. That is the concert. In the concert, all the instruments should play in harmony. Here also, the water molecules, when they are forming a structured water, they give some extra stabilization. And in support of this, I am giving you both theoretical and experimental evidences. One theoretical evidences. When you are doing some reactions with Diels-Alder reactions or cycloadditions reactions with MVK, methyl vinyl ketone, it has been shown that there is a decrease in activation energy, and under that condition, one molecule of MVK is stabilized by 6 molecules of water. That is, each MVK, methyl vinyl ketone, is stabilized by 6 molecules of water. It means 6 water molecules are making a concert. Now, if you change one of them, so one water molecule is changed by acetonitrile, and it has been found that the stabilization is completely lost. It means you are changing one of the musical instrument by some other instrument which is playing in different tune, and the total system, the stabilization has lost. But this stabilization disappears if one water molecule in the cluster is replaced by acetonitrile. It has been done theoretical calculation, and by this it has been shown. So water cluster, a growth of strong water structured cluster is very much important, and that is around the transition state. That is, stabilization of the transition state is taking place in this way. Now the question arises, what about the ketone and ester? For ketone it is happening, but not for the ester. Why not? I am giving you some experimental evidence. Suppose you are doing a reaction of this azomethionylide with a ethyl vinyl ketone and methyl acrylate. And in these two cases, you have raised the temperature. You are doing these reactions, one reactions with this, one reactions with this, between the ketone and 1,3-dipolar here with the ester and the 1,3-dipolar, performing 2 reactions. And you are raising the temperature from 29 to 64 degree. What happens? In case of ketone, the rate was 207 at 29 degree, and that decreases to 82 at 64 degree. So with increasing temperature, 29 to 64 degree, the rate decreases. What about ester? When you are performing the same reactions with methyl acrylate, it is found that if you raise the temperature from 29 to 64, there is no considerable change in rate. This clearly shows that definitely some extra stabilization was there in the case of the ketone. And that's why the ketone was stabilized by this type of growth of strong structured water cluster, but not the esters. So from this concept, we can think that simple 1:1 hydrogen bonding, just single hydrogen bonding, is not always operative. Some cluster of hydrogen bonding is operative, and that is helping the ketones. And that's why ketones becomes the water super. Because in water, this ketone forms a structured water system. It forms a concert of water so that to stabilize the transition state. not for the esters. That's why the ketones, that may be vinyl or alkynyl ketones, those are stabilized by water in the transition states and they becomes the water super. Now we are coming to polarity effect. We know that if the transition state polarity is higher than the ground state, then in water that will be stabilized, so reaction rate will increase. And on the other hand, if ground state polarity is increased than transition state, then reaction rate will decrease in water, in polar solvents. But the question arises, we are not concerned with those, but the question arises, this reaction, say, we have already considered earlier, cyclopentadiene plus isoprene. This reaction is going on, and in water, this reaction is better than in organic solvents. There is no question of polar ends. Then how water is going to stabilize the transition state? Then it was believed, or it was thought that whether solvent, that is water, can induce polarity in non-polar or weakly polar transition state. If we look here in this way, we can. This is working here, say this one. If we look in this way, we may not consider any polarity at these ends, but people believe that in water or in polar solvents, some polarity is developed in the reaction sites in the transition state. That is why the hydrophobic character is completely lost in the reaction sites, in the transition state. And this is the biological chemistry follow this strategy, but the organic chemistry, we don't have so much of evidence with that. I just like to show you one thing, that one example that I have got, and that will help, that support this evidence. Suppose we are considering some tetrazine Diels-Alder reactions. It is inverse Diels-Alder reactions because the diene part has some electronegative nitrogen atoms, and it is the dienophile part. So LUMO of this is going to interact with HOMO of this. It will be stabilized by electron donating group. Whatever it may be. Now we are interested with the rho value of these reactions. For the students, I just like to mention, you just take it into considerations. You may not be acquainted with the rho value of the reactions. You just take it into considerations that the rho value increases. Positive or negative is different things. That depends upon the conditions where the reaction is going on. But taking into consider it, that higher the rho value means higher will be the polarity in the transition state. Higher is the polarity. And if you perform this reaction in different solvents, say in toluene, acetonitrile, TFE means trifluoroethanol, CF3CH2OH, ethanol or aqueous butanol. You see the rho values minus 0.51, minus 0.58, minus 0.1.64, minus 0.1.38. That is in TFE and aqueous butanol. This rho value has high value. Negative, you ignore it. So this has a high value, means compared to toluene, in polar solvent, the higher polarity is developed. So that was actually happened here. You see, some polarity is developed in the reaction sites in the transition state. That we can support by this experiment, that the polarity is developed if we change the solvent from toluene to it is just like ethanol, trifluoroethanol. The polarity is high. So with the increasing polarity of the solvent, the reaction sites which have no polarity or little polarity, the polarity may be increased or polarity may be developed by the solvent. So with these considerations, we can think that in water, the polarity of the hydrophobic ends can be developed. This is the reaction mechanism. I'm not going to that. Now you consider another important aspect, that is the volume of activation. What is volume of activation? Volume of activation is measured by the difference between the molar volumes of transition state and total molar volumes of the reactants in the ground state. That is, in the transition state, you consider the molar volume, and in the ground state, you consider the total molar volume of the reactants. Then this minus this. So if the volume decreases here, then it will have a negative volume of activation. Now, what is happening with this negative volume of activation? It means when you are going from the ground state to the transition state, the volume is decreasing. So you think about the hydrophobic effect. What the hydrophobic effect wants to do? It generates a high pressure on the hydrophobic aggregates. What happens? They try to squeeze So they try to reduce their volume so they can readily reach the transition state. So with negative volume of activation, that those reactions with negative volume of activations will be facilitated in water because of the strong hydrophobic effect. And now you can consider about the endo-exo ratio. Endo means the group is inside, exo means group is outside. In the endo, the volume is relatively smaller than exo. So as in the endo, the volume is smaller, so the negative volume of activation will be higher value for the endo compared to exo. So the hydrophobic effect of water will help to get you more endo product than the exo products. So in this way, we can endo-exo product can be rationalized. Now we are going to discuss the on-water, in-water reactions. Actually, it depends upon the solubility area. But solubility is, if the solubility is less than 10 to the power minus 4 moles per liter, then we consider the on-water reactions. Otherwise, we can consider the in-water reactions. Here some examples are shown that about 23 degrees centigrade, 10 minutes in water. If you carry out these reactions, within 10 minutes it is happening. But for toluene and neat, time is much higher. Here again, toluene time is very long time is required. For water, only 8 hours. These are happening of in-water reactions. Now we are coming to on-water reactions. What is on-water reactions? I have told you that it is very interesting. The compounds, the reactants are insoluble in water. The product is insoluble in water, but the reaction is going on. How? It is a miracle. Actually, some conditions are required. What are the conditions? Listen carefully. First condition is, it must have a liquid phase which is completely different from water. That is, they can readily form a very clear organic phase. They should not mix with each other. Water and organic phase, the liquid phase, they're just oil water. A clear phase would be there. Clear phase of separation will be there. First condition. Second condition, one component will be liquid, definitely, but solid reactions can also react if one of the partner is liquid. Then these reactions can take place. And third one is adequate mixing is required. Under these conditions, the on-water reactions can happen. Now the question is why, how? What is the mechanism of these reactions? I'm going to discuss it today. It was established by Marcus and Young in 2007. They published in JOC, and this is the transphase hydrogen bonding. What is this? I just like to show you a picture here. In the case of, this is the Breslow hydrophobic effect, where the hydrophobic aggregates were formed, water molecules are surrounding it. And here in this case, here is a large hydrophobic surface, not hydrophobic aggregates, but large hydrophobic surface. And there is water. So clear distinction between water and hydrophobic surface. Now you think about the water surface. What is there? At the last layer of water, in the bulk, what is happening? All the waters are tetrahedrally hydrogen bonded. All the hydrogen molecules water molecules are tetrahedrally hydrogen bonded. But in the last layer, the water molecules are not completely tetrahedrally hydrogen bonded because some hydrogens are dangling upwards. Some water layer is here. So suppose oil layer is in the upper phase. So some hydrogen, unbonded hydrogens are, some free hydrogens are there. And it is observed that in water surface, it has been calculated that in per 4 water molecules, there is 1 water molecule with free hydrogen. Per 4 water molecules, there is 1 hydrogen bond that is dangling upward. And so now if you shake vigorously, what will happen? This hydrogen, which are not hydrogen bonded, these will enter into the hydrophobic zone. Once they enter into the hydrophobic zone, it means this just behave like a naked proton, because this proton is no more stabilized by anyone. Here the hydrogens are stabilized by hydrogen bonding inside water. But in the hydrophobic zone, when this hydrogen enters, it becomes a very reactive site. Just you think that you are in a desert and you are just in search of water, in search of foods. Then you are so much desperate. Here also, this proton is very much desperate. This is the reactive sites, and under these reactive sites, the reactions goes on. And if you consider, you will find that this rate of reactions is about 10 to the power 5 times faster. And in case of hydrophobic, Breslow hydrophobic condition, the hydrophobic effect, this rate enhancement was about 600, but here the rate enhancement was about 10 to the power 5 times faster. This is the reactions conditions. Now I am just want to tell you under what conditions, what type of reactions takes place. If the compound is soluble in water, some solubility is there 10 to the power -2, then you can perform reactions between liquid, solid, solid. All types of reactions are possible, and the effects are hydrophobic effect, normal hydrogen bonding, transphase hydrogen bonding. And what type of reactions are going on? Mainly in water reactions, that is through hydrophobic aggregates, and some on water reactions. If they are sparingly soluble, 10 to the power -3 to 10 to the power -5, then only liquid, solid. One component should be liquid. Hydrophobic effect, transphase hydrogen bonding. These are the effects, and mainly on water reactions, because solubility is very poor. So mainly on water reactions, some in water reactions. If very poor solubility, then only liquid, solid. Only transphase hydrogen bonding is possible, and it is called the on water reactions. As the hydrogen is entering into the different phase, it was in the aqueous phase, now it is in the hydrophobic phase. That's why it is called the trans phase. That is from one phase to other phase, the hydrogen bonding, as such the hydrogen is going on there. That's why it is called the trans-phase hydrogen bonding. And Marcus did it. That's why it is called Marcus trans-phase hydrogen bonding. Now I am just giving a few examples. Time is short, I have to finish it. Now you see the products from liquid dipolarified. Here is a liquid compound. So the on-water reactions can take place. You have learned. Here is some solid dipolarified, but some solubility is there. So some in-water reactions can take place. And here some component, some liquefaction. Now here is a very interesting feature. You see, it is a solid, solubility is very low. Here is a solid, solubility is very low. So how this reaction is going on? In water at 20 degree, the reaction is not going on. But at 75 degree, the reaction is going on. How? Because at higher temperature, at 75 degree, you see one component, that is, it has the melting point of 58 to 62. One component has gone into the liquid phase. So as one component is in the liquid phase, so the on-water reactions can take place. So when this, under the reaction condition, this component becomes liquid. That's why it is on-water reactions conditions. Similarly, similar is the case here. You see, this compound has melting point 59 to 61. So at 20 degree, no reaction. Solubility is very low. No reaction is going on. But you consider the temperature 81 degree, then the reaction is going on. It means one component becomes liquid. That's why the reaction is going on. So what we have considered, that in conclusion, we can consider here, when chemists in laboratory or industry seek to choose a solvent for synthesis, water should be at the top of the preference list. We can consider it. If reactants are insoluble in water, it does not matter as long as one component is liquid. If one component becomes liquid, if they are not soluble, if their solubility is very poor, then also the reactions can be performed. If all reactants are sparingly soluble solids, one must be liquefied under the reaction conditions. All are solid, no problem. But if one can be liquefied under the reaction conditions, that reactions can be performed. And that can be done by transphase hydrogen bonding considerations. That is the on-water reactions. So what is the problem? The problem remains with us is that if all reactants are sparingly soluble solids, all are insoluble and could not be liquefied under the reactions conditions. You are doing the reactions in water. Its melting point is greater than water. So it will not be liquefied. Then how this problem could be solved? That problem can also be solved by using micellar medium, but that I am not going to take into account today. But in micellar medium, this type of reactions can be readily done. And finally, I should consider that there is the interplay between the cooperating and conflicting effects of all the factors that we have considered in water. But it is still in a very early stage. That is, and miles to go before we reach. With this, thank you very much for your patient hearing.
Am I audible?
Yes.
Thank you very much, Pandakanda, for such an enlightening lecture on organic reactions in water. The session is now open for any comments, queries, or discussion. I request you please put your comments and queries in the chat box. The students may ask their questions sequentially and please unmute them during this question. There is one question in the chat box made by
Please.
Ashish Kumar Das. The question is, the water hydrogen close to the hydrophobic layer is also positively polarized. Then how can it make?
Excuse me. What is the? Please repeat. Water.
The water hydrogen close to the hydrophobic layer is also positively polarized. Then how can it make way through the non-polar layer? How can this Marcus transphase hydrogen bonding occur?
Okay. No, practically what happening here, if you consider the last layer, in the last layer, all the hydrogens are not hydrogen bonded. If you consider in the bulk, all the water molecules are tetrahedrally hydrogen bonded because those hydrogens are hydrogen bonded with oxygen and the lone pairs are hydrogen bonded with different water molecules. But in the surface, the water molecules, some water hydrogens are hydrogen bonded inside, but a few hydrogens are dangling upward. They are directed outside the water molecules or outside the water surface. And that is actually the source of the reaction type. And those hydrogens, when enter into the hydrophobic system, when those hydrogens enter into the hydrophobic solvent because of the vigorous shaking is a criteria, you consider it. Because of the vigorous shaking, when those hydrogens enter into the hydrophobic zones, those centers become the reactive sites.
Excuse me,
And
Chandrakanta.
yes, please.
Okay.
Please.
Please. Regarding the on-water reaction, you have just mentioned the Marcus transphase, that is naked hydrogen concept. Whether it is this mechanism has been established, this mechanism.
No. Practically, it is the first criteria. In 2007, it has been given by Marcus and Young in JAX.
Okay.
You know. And now miles and miles to go before you get the clear concept. Practically all are now at the infantry stage.
Because without identifying the transition state, how these
No. There is no question of no question of getting the intermediate or like that. But all are now hypotheses. And these hypotheses one day
the concept of naked hydrogen and it enters into the reaction site and
hydrophobic zone. In the hydrophobic zone, that is the main thing.
Yes, hydrophobic site.
Yes.
This is whether I don't know whether it is established or not.
No. Practically nobody knows now. Nobody knows now clearly. Not you.
and the last question, that is whether two reactants are solid, both are solid and insoluble in water. Whether such reactions will be carried out or not.
No.
Both the reactants.
These reactions, when you carry out these reactions in water at 20 degrees, no reaction is taking place because this is solid, highly insoluble. Yes. This is solid, highly insoluble. No reaction is taking place. But whenever no reaction takes place. But if you heat it at 81 degree, then this component becomes a liquid because here melting point is 59 to 61 degree.
Okay.
As it becomes liquid, so it fulfills the criteria of on-water reactions. Because the on-water reactions, one component must be liquid.
Must be
liquid. And there should be a clear distinct layer.
Otherwise, it is not possible.
Otherwise, it is not possible.
Thank you.
And here, this example is also like that. Here also you see, this component has melting point 58 to 62 degree. At 20 degree, no reaction. At 75 degree, this reaction is taking place. These have very poor solubility. Yes, reaction start at 75 degree because at these conditions here, 75 degree, here it becomes liquid. Under this reaction condition, it becomes liquid because the melting point is around 60 degree. That's why one component must be liquid. That is the criteria of on-water reaction.
On-water. Thank you.
There is few comments in the chat box. Gopalandi make a comment. The lecture is very informative and wonderful presentation. Another comment is by Sushant Kumar Nandi, who told the speaker is very good. Is there any questions from anybody else?
Thank
Students?
you.
Yes, sir. I have a question.
চন্দ্রকান্ত অনেক
Yes,
ধন্যবাদ।
yes, please. হ্যাঁ হ্যাঁ
One-
আর কোনো প্রশ্ন আছে বলছে যে একজন প্রশ্ন আছে বলছে
আচ্ছা আচ্ছা স্যার, আই হ্যাভ এ
বলো, বলো,
কোশ্চেন।
কে বলছো প্লিজ
হ্যাঁ, আমি সুশান্ত মান্না বলছি। সুশান্ত মান্না বিধাননগর কলেজ। স্যার ভালো আছেন?
প্লিজ বলো বলো
ইয়েস স্যার, ইয়েস। হ্যাঁ হ্যাঁ, আমি পুরোটা শুনলাম, খুব ভালো। আমি গ্রিন কেমিস্ট্রি
হ্যাঁ।
এটা নিই। তা হচ্ছে বেশিরভাগই তো আপনি যেটা বলেছে পেরিসাইক্লিক রিঅ্যাকশন, ডিল সেলডার রিঅ্যাকশন নিয়ে বেশিরভাগ।
হ্যাঁ এইটাই এটা আমার বলা হলো না একটা রিঅ্যাকশন, মানে যেটা
হ্যাঁ।
বেশিরভাগটাই করেছে কিন্তু ডিল সেলডার রিঅ্যাকশনস নিয়ে। দেখো এখন পর্যন্ত যা করছে তার কারণটা হচ্ছে
হ্যাঁ,
নেগেটিভ
হ্যাঁ।
ভলিউম অফ অ্যাক্টিভেশন, এই সাপোর্ট এই বেনিফিটটাকে নিচ্ছে। দিস অ্যাডভান্টেজ হ্যাজ বিন
আচ্ছা আচ্ছা।
কনসিডার্ড।
হ্যাঁ হ্যাঁ
নেগেটিভ ভলিউম অফ অ্যাক্টিভেশন তো পেয়েছে। কিছু রিঅ্যাকশনস আছে যে রিঅ্যাকশনস গুলো হয়েছে, যেমন ধরো তোমার ক্লেজেন্ট রিঅ্যারেঞ্জমেন্ট কিছু আছে, এই ধরনের কিছু রিঅ্যাকশনসও আছে।
হ্যাঁ।
হ্যাঁ এখন আস্তে
আচ্ছা,
আস্তে
আচ্ছা।
আস্তে ডেভেলপ করবে আর কি, আরো অন্য কোনো ভাবে। তবে মেজর গুলো হয়েছে, যা টেবিল দেখালাম সমস্ত কিছু কিন্তু ওই সাইক্লোঅ্যাডিশন রিঅ্যাকশন, কারণ ওই নেগেটিভ ভলিউম অফ অ্যাক্টিভেশন
তাহলে আমরা
ওই
আরেকটা
নেগেটিভ
জিনিস,
ভলিউম অফ অ্যাক্টিভেশন সাপোর্ট পাচ্ছে। হ্যাঁ বলো।
হ্যাঁ আরেকটু আমি বলছি যে আমরা তো একটা জিনিস
বলো।
পড়াই যে পেরিসাইক্লিক রিঅ্যাকশন ডিড নট গভর্ন বাই এনি সলভেন্ট অর নো সিগনিফিকেন্ট রোল অফ সলভেন্ট। ঠিক আছে, তাহলে এখানে এই
ঠিক নয়, এখনকার দিনে তো ঠিক নয়। ওটা তো
হ্যাঁ
অবশ্যই
এখন আর
ঠিক না।
ওরকম ভাবে আমরা বলতে পারবো না।
না
হ্যাঁ।
না না না, ওটা তো বলা, হ্যাঁ অনেকদিন আগেই ওটা বলা বন্ধ হয়ে গেছে। আমরা তো ছোটবেলাতে শিখলাম। হ্যাঁ ঠিকই।
আচ্ছা, থ্যাংক ইউ স্যার, থ্যাংক ইউ। খুব ভালো লেগেছে
হ্যাঁ,
প্রেজেন্টেশন। ওকে স্যার।
Hello.
ভালো।
হ্যালো
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 প্লিজ।
হ্যাঁ
হ্যাঁ প্লিজ
আমি
প্লিজ
আমার
আই ক্যান হিয়ার।
হ্যাঁ আমার কিছু বলার আছে। হ্যালো,
হ্যাঁ বলো, কে প্লিজ বলুন, প্লিজ কে বলছেন, আমি বুঝতে পারছি না। প্লিজ
আমি শিবপুর দীনবন্ধু কলেজের রসায়ন বিভাগের দায়িত্বে আছি। আমার নাম আশিস দাস।
আচ্ছা
হ্যালো, আমার
Hello,
বলার
hello.
একটা কথা। হ্যালো হ্যালো
কে বলছেন প্লিজ একবার শুনতে পাচ্ছি না। হ্যালো
হ্যাঁ আমি শিবপুর দীনবন্ধু কলেজের
হ্যাঁ বলুন কে
রসায়ন বিভাগের দায়িত্বে আছি।
ও শিবপুর। আচ্ছা
হ্যাঁ
আচ্ছা ঠিক আছে, বলুন।
আমার নাম
বলুন,
আশিস
বলুন।
দাস। হ্যাঁ প্রথমে
আচ্ছা,
বলি, আপনার লেকচার
বলুন।
শুনে আমার ভালো লাগলো। একটা কথা খুব মনে পড়লো, জানেন, দেয়ার ইজ নাথিং মোর প্লেজেন্ট দ্যান আ গুড
বলুন।
লেকচার। একটা ভালো লেকচারের থেকে আনন্দের আর কিছু নেই। হ্যালো,
ভালো লাগলে আমার ভালো লাগে আর কি, সবার ভালো লাগলে তো ভালো।
হ্যাঁ একটা প্রসঙ্গত একটা কথা বলি যে আমি এরকম
হ্যাঁ বলুন।
আমি নিজে এরকম অ্যাকোয়াস মিডিয়ামে কিছু প্রিলিমিনারি সিনথেসিস করেছি।
আমি কথা কেটে যাচ্ছি, বলুন।
আন্ডার গ্রাজুয়েট
আচ্ছা।
ল্যাবরেটরিতে ফেসিলিটি তো সেরকম নেই যে আমি অন্য কোনো কিছু নিয়ে করতে পারি, জলে করলেই সেটা ভালো হয়। তো আই অলসো চুজ দ্য অ্যাকোয়াস
সে তো
মিডিয়াম
বটেই।
and I could do something. কিন্তু যেটা দরকার আমার, স্যার আপনার
না।
কন্ট্যাক্ট একটু দরকার, ডিসকাস করুন। কন্ট্যাক্টটা আমি কিভাবে পাবো?
হ্যাঁ আমাকে ফোনে কথা বলুন, কোনো অসুবিধা নেই,
হ্যাঁ ফোন
কোনো অসুবিধা নেই। আমি
আমি
অলওয়েজ অ্যাভেলেবেল। যদি কারো কিছু একটু ভালো লাগে, যদি আমাকে দিয়ে কারো উপকার হয়, আমি খুব খুশি হব, আমার নিজেরও ভালো লাগবে।
কিন্তু আপনার ফোন নাম্বার বা ইমেইল অ্যাড্রেস আমি কোনোটাই জানি না স্যার, আমি পাবো কি করে?
আচ্ছা আমার আমি কি এখানে বলে দেবো?
হ্যাঁ এখানেই বলুন স্যার, আমার মনে থাকবে। হ্যাঁ ফোন নাম্বারটা বলুন।
869 বলছি 869
হ্যাঁ
781 4010
7814010
869
হ্যাঁ
10। হ্যাঁ আই রিপিট 869 781 4010।
থ্যাংক ইউ স্যার,
ঠিক আছে?
থ্যাংক ইউ।
আচ্ছা
Is there any more question? Is there any more question? So there is no more question. So let us move on to the valedictory
Okay.
session. And for this, I would like to refer Dr. Sheikh Anand Mondal to take over this session. Ananda, please take over.
Okay. Am I audible? Am I audible?
Yes. Yes.
We are
Yes.
now almost
Yes.
We are now almost at the end of the third one of our proposed series of 5 such webinars. It is customary to give vote of thanks to all those who are involved in this webinar to make it successful. And I now have the honor and privilege to present the vote of thanks. First of all, I express my heartfelt gratitude to our distinguished speaker, Dr. Chandrakanta Bandyopadhyay, who has kindly accepted our invitation and has delivered an insightful, flawless lecture on a very important topic in organic chemistry under UG PBCS course of West Bengal State University syllabus. Next, I thank our Honorable Principal Sir Dr. Sanjeev Kumar Saha for his inaugural speech and also for being the patron of this webinar. I also take this opportunity to thank our IQAC coordinator, Dr. Moinak Rai, for sharing his valuable thoughts on our program. I now express my sincerest gratitude to all the members of the technical team, Professor Chinmay Biswas, Professor Jyotsna Nath, without whose hard work and perseverance this program would never have been possible. I also thank all the teachers of chemistry department of Rishi Bankim Chandra College, Dr. Ratna Datto, Dr. Gopa Nandi, Dr. Soma Sen, and Dr. Suranjana Propayat, and Dr. Devodina Mitro for their valuable suggestions at each and every stage. Last but not the least, I thank all the participants who have shown interest in our program and have joined us today to make this occasion a success. Thank you all. Stay safe and stay healthy. I now declare the webinar to be over. There is an announcement to be made regarding the feedback form. All registered participants are requested to fill and submit the feedback form. The link will be posted on Google Meet chat box now. Thank you all.